Hey y'all, I'm trying to get everything posted right now. I think this is the correct link that I just pushed out. So we'll see if you guys will be joining me here in a second. Let's see here. I don't know what's going on right now. I hope you guys can hear me. Here, I want you guys. Yes. Okay. Alrighty, I did that. Looks like I'm live. Oh, okay. You can see the back of my, that's my fancy living room. There you go, kids. Don't really know how to get that to see me. So there you go. That's what my living room looks like. You can't see my Christmas tree. That corner over there. Lovely. I hope you guys are doing well. It doesn't really matter that you can't see me. You guys are going to be able to get some answers from me. So what I'm going to be doing is my screen, because as I go through, let's see, I want this guy here. As you guys look through, or what I'll be doing is I'll be answering the questions that you guys left for me using this list here and this thing called a web whiteboard that's pretty darn sweet. So that's kind of what we got rocking going on today. Sorry that other thing didn't work. I hope you guys are able to see what's going on right now. A couple of things about the final exam. Sorry, I'm typing you guys. Just to know if you guys let me know if the link is working or not. A couple of things about the final exam. It's definitely going to take you guys probably about the full 90 minutes. So I would just make sure that you come prepared to kill that exam and know that you guys are going to do amazing. You're totally ready for it. I would definitely start on the short answer and do the multiple choice second. I think the multiple choice is way easier than the short answer, to be honest with you. So answer is, yeah, Nicole, I know it's only a blank screen. I'm on a web, ooh, that's not what I wanted. I'm on a web whiteboard right now. So what you guys will probably be seeing is my web whiteboard. Okay. So what I'm going to be doing right now, guys, is, like I said, I would definitely start with the short answer first, as it's going to be some explaining and some math. The multiple choice is going to go fairly quickly, I believe, but it's up to you guys, whatever you guys kind of want to hang out with or start with. But I think you guys are definitely prepared. So what I'm going to be doing is I'll be running through these questions that you guys had, and I will be using this thing called the web whiteboard, which is this blank screen here, to answer some of your questions that I can't answer in the doc. So we're going to go ahead and start with topic 1, atomic structure, periodic tables, and trends. So the first question I got was, for question B, use the information below to make the atomic symbols for the elements. It says A is 14, Z is 6. So if we do just a quick review of the atomic symbol stuff, guys, remember you've got X as your element symbol, and then if we, let's see here, A and Z. So A is going to be your mass, and Z is going to be your atomic number. So remember your mass, protons, and your neutrons in total that you have. And Z is going to be your atomic number. And that's going to tell you the element that you have. So if I know Z equals 6, what I'm going to do is I'm going to look at my periodic table, and I'm going to find the atomic number for 6, which I know is equals carbon. So as I'm building out the symbol, C is going to be where X is. I'm going to put 6 down here. That A equals 14, so that tells me that my mass number for this isotope is going to be 14, which means it has a total of 14 protons and neutrons. So if I want to figure out the pieces, remember the 6 tells me total number of protons. So I do 14 minus 6, which is that has 8 neutrons in its nucleus. So if I was to draw a picture of what that atom looks like in its nucleus, I would see 8 neutrons, 5, 6, 7, 8. I would see 8 or 6 protons. And that would be inside the nucleus. And then on the rings, remember, for our isotope symbols, the protons is going to equal the number of electrons. So then in the rings, I would build out 6 electrons total. So the reason this number is not 12.011 is because that mass is the average atomic mass from the periodic table of the elements. When you're doing isotope symbols, the mass will be given to you either in the problem or will give you number of protons and number of neutrons, and you just have to add those together. So that is my answer to this very first question here. So I hope that has answered the question for whoever asked it. It definitely lags. The live stream is a little bit behind the live stream. I think they do that in case, I know, but let's hope nothing happens in our chat today. So I'm going to go out. Alrighty, move on to the next question. So the next question, it says, can you do an example that's similar to the last part of question D? Which metal is more reactive, SR, BE, and why? I'm confused how to determine what metal is considered more reactive. And then it also talks about what influences more, atomic radius or ionization energy. What we'll do for these ones here is they'll be fairly straightforward. If we're asking you something that's talking about elements being more or less reactive, we're going to be very straightforward. It's going to be something that will either be the trend across a row or it'll be the trend across down a column. So it'll be very, very easy because the atomic radius trend and the ionization energy trend will mirror each other. In the real world, ionization energy will determine reactivity because it's how much energy you need to remove an electron, and that we know is what determines a metal's reactivity. So this guy here is the key player that will determine whether or not you're reactive or not. But for the test tomorrow, Tuesday for some of you guys, Wednesday or Thursday for the others, it'll be very, very, very simple for you to figure out, are we looking at something that is down a row or across a column? This one here, can you do an example? What's more reactive, SR, BE, and why? How you determine which one's more reactive? It's going to be the guy that's the biggest. So atom is always going to equal more reactive. The reason that that bigger atom is going to be more reactive is because those electrons end up so far from that nucleus that they're not able to be kept in by the atom, which is why it has a low ionization energy, because it's going to be very easy to remove it. That also means it has a low electronegativity because it's not good at attracting electrons. So those two things together, the low ionization energy and the low electronegativity, are what are going to allow that atom to more easily lose that electron. So anytime I'm asking you between two atoms, which one's more reactive, it's always going to be the guy that's the biggest. So if you can figure out which one is the bigger atom, that's going to be the guy that loses the electron easier. Equals low attraction to electrons, which is going to equal easy to lose. So it equals more reactive. That's just kind of a general summary, but you can throw in those words like electronegativity, ionization energy to really beef up your answer to get the full points on that guy there. So I hope that that helps that question here. What's the charge of transition metals? When you're trying to figure out what the charge is for transition metals, what you're doing is you're looking at that back chart in the middle side of your periodic table. So if you flip over to the back of your periodic table, you'll notice that that middle chunk has the common transition metals we use in class, and it'll give you a couple of charges to choose from. I found this guy here just online just to give you a visual example of that. But if we were asking you, for example, the charge of iron, iron could be +2 or +3. Or if we were asking you the charge of copper, copper could be +1 or it could be +2. So how you figure out which one it is you have to look at the ion that it's paired with. So if I was to give you guys two examples, let's say I asked you to figure out the charge of iron, what you would want to do is you would want to look at what is the iron paired with. So if we had something like FeCl2, FePO4, how I figure out the charge on the iron is I look at the negative piece that's going to dictate its positive charge. So if I look at FeCl2 and I build out one of those handy dandy charge charts, I've got one Fe in my compound, 2 Cls. Because I know my iron could be +2 or +3 from the back of my periodic table, I have to use my Cl to help me out. Because chlorine's in column 7, more electron to be octet happy, So each chlorine is going to take on a -1 charge. My charge chart, because there's 2 chlorines here, I know that it's a -2 total. I also know that in order for me to have an ionic compound, my total positive negative has to add up to 0. So that means my iron, in this case, has to be the guy that's a +2 charge, because +2 and -2 equals 0. So in this compound, it's 2 guy. If I look over here in this compound, FePO4, and again, I do my charge chart, I've got 1 Fe, and PO4 is 1 PO4 polyatomic ion. It's the phosphate ion. PO4 on the back of my periodic table, I can see that he is a -3 charge. So that means each of these chunks is -3, 3 for my negative charge. Again, I know it has to add up to 0, which means in this case, my iron has to be the +3, equals 0. So that's how you would figure out the charge of transition metal, is you would look at the negative anion that it's hooked up to, and knowing that all ionic compounds have to be neutral, you can just do a little bit of logic or a little bit of math to go ahead and figure out which charge it actually is. So that's how you determine transition metal charge. I hope that helps the question, people. Alrighty, and the last question I got was how to read a graph to determine the periodic trend across a row and down a column. Let's go ahead and, ooh, that's the Heisfeld graph. Let's see if I can go ahead and pull one of these guys in here. That web light. Here we go, it looks like a decent one. Let's go ahead, copy image. Can I paste this into here? Nope, I can't. Okay, well, we can go ahead and we can talk about it here. Okay, so when you're trying to read, let's do it in here. Let's just do this. Copy image address. Okay. All right, so if we answer this question here, how to read a graph to determine a periodic trend. I pulled the atomic radius trend, which is the one that we had you guys graph in class. And so this guy here is very similar to the one we did in class. So if we're looking at how to figure out where the columns are and where the rows are, it all kind of hinges on your ability to read the graph. So atomic number here is on the x-axis and atomic radius is on the y. So we can see from our graph that as the atomic radius increases, the bigger atomic radius will be towards the top of the graph, and the smaller atomic radius will be at the bottom of the graph. How we figure out the trend for a row versus a column, you guys are cracking me up. All right, so if you guys try and figure out the trend for a row versus a column, what we're doing is we're going to look at atomic number. So if we look for the trend across a row, we're going to go ahead and we're going to look at lithium's row, which is lithium to neon. So lithium is atomic number 3. So if I look at this graph here, you've got number 3 right here, which is this top dot. And I know that the end of its row is neon. Okay. And if we look at the neon, which is atomic number 10, it's down here, this last dot. So that means this 3 to 10 right here is one row on the periodic table. So if I look again, if I go to the next row, that's going to start with sodium, which is atomic number 11. And then I look at the end of the row, which is, I don't have a periodic table in front of me. I think it's argon with atomic number 20. Nope. Neon. Is argon next? I think argon's next, which is atomic number 20. Here is my next row. And again, we've got 19 to about 38. There's my next row, 37 to about 54. That's xenon. Here's my next row. And then 55 to radon, which is my next row. So when we're looking at this graph, our rows are going to be here from the top And then when it peaks again, here's another row, top to the bottom. So if we're looking at how this graph is read, you can see that from the left side of the row lithium to the right side of the row neon, the trend is downward for atomic radius. Same thing here, 11 to 18, it's down, 19 to 38, it's down, or sorry, 19 to 36, it's down. Across all our rows, the trend is down. Now, how you figure out what the columns are is you look for the things that are in the same column. So if we start with lithium again, which is atomic number 3, and then we figure its column, you can see that next after lithium is going to be sodium at 11, 18, then rubidium at 37, and then cesium at 55. So if we look at all of these dots here, you can see the general trend for this is upward. By the rows, I think it's easy to find the columns, because the rows, you'll start from 3 to 10, 11 to 18, ETC, and then the column, then you just find atomic number. So there's column 1, and if we look at the noble gases, that's 10, 18, 36, blah, blah, blah. So that would be the noble gas. But we can see again, generally, and is upward for this. So that's kind of how you read a periodic trends graph, is you just have to figure out, looking at atomic number, where your rows and where your columns are. That's a terrible explanation. I got distracted by the chat. We only use the chat for important questions. I agree. If you do have a question that pops up while I'm explaining something, feel free to jump in on the chat and ask it. I know it's a little bit laggy in the live stream, so I'll come back and answer it, even if it's after the fact. And that's all the stuff again to topic 2, which is bonding, Lewis, and states of matter and intermolecular forces, a whole plethora of stuff. So I'm going to go ahead and find some of these a little bit. We're going to cut this question out of here because this kind of goes with this guy up here. I'm actually going to do this. The very first question here. Okay. Alrighty. So if we are looking at this stuff here, the first couple of questions that I'm going to deal with are all kind of dealing with the idea of determine strength of a bond or strength of an intermolecular force. So to answer this first question here, collect data to determine the strength of a bond or of an intermolecular force. This goes back to the interactions phenomena lab that we did back in unit. So that's going to be where you're just going to collect either melting point or boiling point data, and that's going to give you a whole slew of information about the strength of the forces in that molecule. So pretty much you want to get melting point or boiling point data, and then the strength of the attraction is going to determine the melting point or boiling point. The general rule of thumb is the higher the temperature, the stronger the force. So pretty much you're asking any question or answering any question about bond strength, force strength on your final exam. It's pretty much all going to be based off the data numbers that you have. So the higher the number, the stronger the attraction. So if we look at question number 2, must have the lowest ion charge and why. If we remember back to the magnet lab that we did back in this unit where we play with the different magnets, we saw that the stronger the ion charge was, meant that it was a stronger magnet. It was much more attractive. So that means if I'm I'm going to have a really high ion charge. So I am going to have a low ion charge if my magnet is weak. So a weak magnet, energy to disrupt the bond, which means my melting point and boiling point would be a lot lower. So if we look at these three options here, which has the lowest ion charge and why, we're looking for the lowest melting and boiling point. And so we can look here and see that compound A has a melting point at 660, which is lower than the rest. And it has a boiling point of 1304, which is lower than the rest. So that means that this guy here has to have the lowest ion charges because his boiling point are the lowest options possible. So that would be the answer to that guy there. this question here, it's kind of like a sub-question to this. It says C has a higher melting point, but B has a higher boiling point. That would be a super tricky question that I would not ask you on the file, because the boiling point of C is lower than the boiling point of B. That means that B must have the stronger attractions, because when you boil something, you're completely breaking free whatever substance you have. So we think about states of matter. I'm going to go ahead and draw a picture on the board here. So if we think states of matter is kind of 3 beakers, if I'm a solid, remember super, or so I'm just reaping it super organized. If I'm a liquid, it's organized. But the big thing about liquids, a lot of attractions. These are supposed to be dots, but they're not really dotting. Where if I'm a gas in that capped container, no more attractions. So if we think about kind of the difference between a solid, a liquid, and a gas is not attracted to anything. So in order for us to boil, we have to break whatever attractions we have. So if you're really looking for what the strongest one you have is, you want to look specifically at that boiling point data, because the higher the boiling point, the harder it is for it to break free of the attractions, meaning that it has the strongest attractions possible, because they're not present in the gaseous stage anymore. So for us to go from the liquid to the gas, we have to break whatever attractions we have. So the more energy it takes us to boil, the stronger those attractions are. So I hope that helps with that a little bit. That was some awesome handwriting I just had over here. My bad, guys. I'll promise to write better a little bit later. Okay, and I think I hit number 4 with my answer to 2 and 3. So if you guys have any questions about using data or determining strength of intermolecular force or strength of ionic bond, feel free to pop into the chat box over here, and I can get that to you guys here in a second, if you guys throw any questions in there. The next question we've got is about the octet happy rule. Remember, octet happy means having 8 valence electrons. So 8 equals octet happy. So the 2 exceptions are going to be hydrogen, 2 valence electrons to be octet happy. Because remember, we can only hold 2 electrons in that first energy level, so he's happy with 2. And the other guy is boron, 6 valence electrons to be happy, because he only has 3 in that outermost energy level. He's not strong enough to bring 5 in to fill his shell, and he's also not going to give up the 3 because he has a really strong electronegativity for how small he is. So he's just happy sharing those 3 electrons with other things, which means he's only happy with 6 electrons. So those are going to be the kind of the exceptions to the octet rule. So the difference between a Lewis dot structure with ion bonds, that's going to go into some drawings again. So the big thing to tell you the difference is, if you're ionic, you have to be made with metal. Oh, that's not how you spell metal. Oh, there is an eraser. Look at that. Well, that's a really small eraser. And then if you're covalent, that means you're nonmetals only. So if we think about the Lewis dot structure for these things, so if I was to draw the Lewis dot structure for something easy, I'll do one that's a little bit more complex. Let's look at calcium chloride versus, let's do something like carbon dioxide over here. Look at these 2 guys here, because I've got a metal and a nonmetal. Remember, based off of electronegativity, your metals will always lose electrons. So our Lewis dot structures are going to look a little bit different. So calcium 2 with 2 valence electrons. Oh, I'm going to change color here. Is in column 7. And so he wants 1 more valence electron, which is why, there's 2 of them in this compound, because the calcium wants to lose the 2 electrons it has to the chlorines. So to draw our Lewis dot structure to give our final answer, because our calcium is going to lose its 2 electrons, those 2 electrons go away, and now because it's got 2 less electrons than it started with, are all +2 ion charge because it now has 2 more positive protons in its nucleus. Now to draw our calcium, we put a big 2 in front, and then we're going to put brackets because we want to show that all of these electrons, chlorine, and I can really choose color coding for this. And for your final exam, if you want to have colors, you absolutely can. So, and I would show the 1 dot from the calcium that it takes in, which is why it takes on a -1 charge, because each chlorine extra electron, so it's a -1. So this would be how you would draw the Lewis dot structure for something ionic. You would have the metal with its positive charge and the nonmetal with its negative charge. If you have multiple of them in your compound, you would just put a large number in front of the ion to show that how many you have. So in this case, I've got 2 of my chlorine in that compound. Over here to the covalent idea, and remember in covalent compounds, they share electrons because they're nonmetals. They all have high electronegativities. They would all like to gain electrons. Because their electronegativity is so high, they're not going to be able to give them up to each other, so they share them through the covalent bond idea. So how we would draw something like this is play connect the dots. Carbon, oxygen, oxygen. Carbon's in column 4, so he's going to start with 4 dots. Oxygen is, so he's going to start with 6 dots, and then we're just going to simply play, ooh, sorry, Pri, I just kicked my dog in the head. We're just going to simply play connect the dots. Lone electron here and this lone electron here can be shared. This lone electron here and this lone electron here can be shared. And this guy can be shared. And this guy can be shared. Now remember, on your final, you can't kind of show these whoop-de lines. So what we're going to do is we're going to go ahead and we're going to move these into the middle in our final answer. So with 4 dots, a double bond to the carbon, double bond to the other O, sharing the electrons. And this would be our final answer. So covalent Lewis dot structures will show sharing of electrons through bonds. Ionic Lewis dot structure of electrons through your positive and negative ion charges showing. That helps those of you that had that question. Yep, and I see kind of some in the questions. Carbon is not an exception to the octet rule. Carbon has 4 electrons, so it's going to want to share those 4. So carbon won't make any ions, which is maybe what you're thinking about, Ryan. Carbon doesn't make a positive or negative ion ever. It'll just share the 4 electrons that it has, but it always wants to have 8 to be happy. I also have a question, how many multiple choice questions are on the test? I do not remember exactly how many multiple choice there are. I want to say it's like something in the middle, like I must say it's like right around like 35, maybe 35, 38. And then the short answer is, I think, like the answers, but some of them are, are like, the drawing ones. Like if you're drawing like this, there might be a couple of different ones that you're doing for the same problem. But I've taken it myself. I time myself taking it. The 90 minutes you have should definitely be enough time. I'm not going to tell you how long it took me to take it because you guys are going to get mad at me, and I don't, because I want you guys to like me, because I love you guys. I also miss you, by the way. I hope you guys are doing really well. Okay, and then that is number 6 here. And then for number 7, covalent bonds, do you have to write the compound with the brackets and charges? No. For covalent bonds, you do not have to do the brackets and charges. For covalent, what you need is you absolutely need to show the electrons being shared with the lines. That's the important part for the covalent guys. These guys right here, these shared electrons. That's what makes a covalent compound covalent between that. What makes an ionic compound ionic is these guys here, the transferring of the electrons between the metal and the nonmetal, resulting in your positive and your negative charges. So that's kind of the big key takeaways, the big key things to keep in mind. If you ever see something ionic with a metal and nonmetal, you'll have to see positive or negative charge. Covalent, you need to show those electrons being shared. Questions? And that is through topic 2. So on to topic 3, balancing. And clear this. Alrighty. And let's get this question over here. So AgNO3, AlPO4. So I'm going to go ahead and do this balancing guy here for us. Is it again? AgNO3, AlPO4. G3 plus AlPO4 gives you Ag3PO4 plus Al. Oh, I did not leave myself enough room. 3. Okay, so I'm going to go ahead and I'm going to balance these guys here, but I saw a quick question pop up. Yes, Julia. C2H3O2. No. Okay, so Julia, yes, CH2O is covalent. And then Brennan, we did not have time to make a final exam review answer key. However, with the exception of the last unit, every single question came from a previous unit review answer keys. So if you use the ability to filter by units, if you click like unit 2, only the unit 2 stuff would come up. And then you could just choose that test insurance review guide and the answer keys there. So all the questions come from one of those answer keys. So you should be able to find the answers just in the stuff that you guys have. All right, balancing. I'm happy someone chose this one to balance because this is a toughie. So let's go ahead and let's do an RP chart for this. Our RP charts are to count our reactants in our products. So if we think of the things we have here, I've got an AG, N, O, I've got an AL. Ooh, I did not leave myself enough room. I'm going to go ahead and I'm going to delete this out. AgNO3 plus AlPO4 gives you Ag3PO4 plus NO3. All right, RP chart. So I've got Ag, I've got N's, O's, Al's, P's, and O's. Now the tough thing about this guy here is we got polyatomic ions all over the place. So there is a cheat that I didn't tell you guys during the balancing unit that I'm going to tell you guys now because I feel like you're ready for it. So see how I have an NO3 side and I have that same NO3 polyatomic on this side? What I can do is I can count them as an NO3 piece, but you can only do that if you've got the exact same polyatomic on both sides. And I can do the same thing with these PO4s. So I've got a PO4 on one side. Go back to black. And PO4s. So because I've got PO4s on both sides, I can count them separate too. So now instead of having to count AGs, Ns, Os, Al, Ps, and Os, what you can do is just count AGs, NO3s, ALs, and PO4s. And the reason we can do this is because of the idea of the double replacement reaction. We know in a double replacement reaction, your positive ions are going to switch partners because this is just a double replacement. My Ag positive ion is going to end up with my PO4 on the other side. That polyatomic ion doesn't change. So you can go ahead and use this cheat to keep track of the different pieces that you have. So if I go ahead and count, I've got one Ag on this side. I've got three Ags on this side. I've got one NO3 on this side because there's nothing in parentheses. But over here, I've got three NO3s on this side. Ooh, that was really bad, 3. Over here, I've got one AL. And then on this side, I've got one PO4 and one PO4. So I can see that the only thing that I don't have that are matching are my AGs and my NO3s. I've got 3 AGs and 3 NO3s. So what I can do is throw a big 3 in front of this. This compound will change this to a 3, and 3 times that NO3 will change this to a 3. And now you can see that these check, and these check. So if you have something that has super complex polyatomic ions, if you have the exact same one on both sides, polyatomic piece makes it so much easier to balance. All right, and then I know the next question was about the halvesy rule. So combustion. Combustion is definitely a tough one. So let's see if I can get you guys the toughest of the tough. Let's do 2H5OH plus O2, CO2, and H2O. Okay, this one is going to be the toughest of the toughest combustion for one reason. Compound, we've got another O. So I'm counting O's in 2 spots in both sides of the reaction. So that's going to make it the hardest type of combustion to balance. So this one I definitely recommend an RP chart for. Ones I've got C, H, and I've got O. And I think it's really important that you count the O's separately for this, because it's going to make it, I'm going to go ahead and give myself a little bit more room here. Undo. Okay. C, H, I need more space to count my O's. Okay, I think it's really important that you count the O's separately because it's going to make it very easy for you to balance based off of changing. So if I count C's, I've got 2 C's on this side. H's, I've got 5 plus 1, which is 6 in this first compound. I've got 2. If I count O's, I've got 1 in that first compound. I've got 2 in that second compound for a grand total of 3. Over here, I've got 2 in my first compound and 1 in my second compound of 3. So right now, the guys that don't match are my C's and my H's. So I'm going to go ahead and make those match first. You never, ever, ever want to do your O's. In this case, our O's match already, but that's not always going to be the case. You always want to save your O's for last in a combustion reaction. So you want to start with your C's and H's first. And you want to make sure those match perfectly. 2 C's on my reactant side. So to get my C's to 2 on this side, I'm going to put a big 2 in front, because 2 times this compound would give me 2 C's. So this becomes a 2. O's. 2 times 2 is 4. So I'm going to change, this was 2 O's here, now it's a total of 4, and 4 plus 1 gets me to 5 O's on this side. It's okay that they don't match, we'll go ahead and balance them at the end. H's. I've got 6 on this side, I've got 2 on this side, so in order to get myself times 6 to 6 by 3, because 3 times this compound means 3 times 2, H's. So now my C's check and my H's check, but again, I've changed my O's. 3 times 1 is 4 plus 3 is a total of 7. So what that means is on this side, I need to get myself to 7 O's. So that means I want to turn this 3 into a 7. So if I look at the compound that I have, I don't want to change any of these numbers, because if I change these numbers, that would change my C's and my H's, and those already match. So I want to try and keep this a 1. So if I think about math, 7 minus 1 leaves me with 6. So I want to turn this 2 into a 6. And I can do that. 3 times 2 is 6. 6 plus 1 is 7. So now this is a balanced reaction. So this one is super hard because you've got the O's in the 2 spots. One with the idea of the halves-you rule. So I think if we do, C3, H6. I have to do small numbers because I'm exhausted, just like you guys are. Okay, so this one will be one with the halves-you rule in it. RP. So I've got C, H, O, and again, I've got O's in 2 spots. So I'm going to kind of draw my divider line so I can keep track of my O's easier. So on this side, I got 3 C's, and I got 2 O's. On this side, I got 1 C, I got 2 H's here, and 1 O here for a total of 3. So now we're going to go ahead and we're going to balance. To make my C's equal, I've got 3 C's here. So if I put a big 3 in front of this compound, 3 times 1 is 3 C's. So those check out now. 2 is 6, and 6 plus 1 gets me to 7 O's on this side. It's okay that they don't match, we'll balance at the end. On this side, 6, I put a 3 in front because 3 times 2 is 6. So those check out now. And 3 times 1 is 3. 6 plus 3 is 9. So I've got 9 O's on this side, and I want to make this side 9 O's. Number times 2 does not get me to 9. But if I put 4.5 in this little spot here, 4.5 times 2 does get me to 9. And now all my elements check out. So what I can do is I can take this entire reaction, I can multiply it by 2. So every coefficient would get doubled. So my new answer, I'm going to write up here, 2 C3 plus, oh, not 8, that would be 9. Oh, yeah. I blame my reason for not being able to do math. O2s, 6 CO2s, H2Os. So that's when you have the halvesy rule. When you have a number in here that you can't get to because it's an odd number, you just put the halvesy in to make sure that all your elements are now the same number on both your reactant and your product side. Then you multiply all the coefficients by 2. So everything gets doubled. All right, and I hope that helps with that. Okay, I see a couple of questions in the chat that I'm going to address real quick before I go into topic 4. To answer Jenna's question, no, Jenna, you don't have to know density and conversions. Those will not be covered on this final exam. We'll be going back to those types of math conversions early in second semester. So you don't have to do any density math or anything on the final. Julia, there is not a lab present. We didn't want to have a sub set that up and take care of that, but there is definitely using data to determine an answer. So there will be lab application questions, but there's not going to be you guys actually doing a lab. Our state, technically, yeah, we do need states to matter in that first question in topic 3, but we were just doing a balancing problem. So that doesn't have solid, liquid, gas, or aqueous. Ryan, I like your explanation of the halvesy rule. Well done. Joey, no, the test does not specify if you're making ionic or covalent. You have to know whether it's a metal or a non-metal. So it does not tell you. That is a skill you definitely have to know. Oh my gosh, I can't type. I apologize for my inability to type and or talk right now. On to topic 4, which is reaction rates and equilibrium. I'm not shocked. This is most questions. I get the whiteboard ready to go. My husband's doing well. Thank you for those who have emailed and asked. We are doing pretty well here. He is kicking butt at physical therapy, which is, and yeah, I'm doing the best I can to make sure him and my daughter don't go crazy. Okay, on to topic 4, reaction rates and equilibrium. So what does increasing the temperature do to the rate of chemical reaction? Explain based on what you know, based on collision theory. So this goes back to the idea of the glow sticks. So I'm just going to put like hint, think glow sticks. You want to think about that glow stick demo? I can find a good picture here. I'm going to pull this. No, is that what I do? Sorry. Okay. So when we think about the glow stick demo, we saw that in the glow stick in the hot water, it glue a lot brighter because we know the reaction's happening faster, but why exactly is the reaction happening faster? It all comes down to the idea of collision theory. So we know that in order for a chemical reaction to in order for a chemical reaction to occur, we have to have the reactant particles collide with the right energy and the right orientation. So the first thing heat does is it just makes everything move a lot faster. So you're increasing the number of collisions occurring. So that's the very first thing that happens. Increasing the movement of the molecules. Not only are you increasing the number of collisions, you're also increasing the speed of the collisions. So when we think about that activation energy barrier, when you think about that little hump that to make the products, if you're making the molecules move faster, at a lot higher energy, so you're more likely to hit the right amount of activation energy in that collision. So if we think about the two metal spheres that I was banging together that made the sparks, every time I hit them, they didn't necessarily make sparks. If I was able to somehow make my arms move a lot faster, a lot more consistently, aka be just much stronger than I am, I would have made sparks almost every single time. So when you're heating something up, that's essentially what you're doing. You're making everything hit a lot more frequently and a lot of solutions that meet the activation engine. So I hope that that helps you guys with that one for number one. For number two, energy impact whether or not a collision will result in product formation. Give an analogy to support your answer. I'm really sorry that I make weird noises when I do Google searches. I apologize for that. Okay, I'm just going to pull these in here. No, that's not going to work. What? Don't tell me that. Ah! We'll just do this. Cancel. Sorry, I tried to put. Okay, here we go. Let's go ahead and put that one in there. Okay, so when we think about, don't worry about this like with enzyme, without enzyme business. Just think about the idea here of the hill, right? I'm not going to do the analogy idea to talk about just the bump here. So the higher the activation energy, the harder the molecules have to collide to hit. The lower the activation energy, less energy the collision needs in order to get you to make product formation. So you just kind of have to know that the higher the activation energy, the harder the molecules have to hit. The lower the activation energy, the less the molecules need to hit. So the activation energy just determines how much energy you need in order for products to be made. First, okay, yeah. Hope that helps. I'm going to look at some of these chat questions coming up before I do number 3. Okay. Jenna, no, you can't use your periodic tables because you guys get to write lots of things on them. So you have to use the same ones we've been using all year, which are the ones in the little sheet protectors. So those ones will use our periodic tables. Julia, to answer your question, if there are more than 2 elements in a compound, it is not automatically covalent. You can have a polyatomic ion. So I'm going to go ahead and bust over to this, Julia, to answer your question here. So if you have something like CH2O, this would be covalent, all nonmetals. Whereas if I had something like O3, here I have, but because Na is a metal, this is a positive charge, which means this has to be a negative polyatomic ion. So you can't just use that rule that if there's more than 2, it's got to be covalent, because those polyatomic ions in the back of your periodic table throw that out of whack. Because we can stick those things with metals, and then you'd have 3 different elements or more depending on the polyatomic ion in that compound. The rule to know is if you have a metal as the first element, it's got to be ionic. Okay, that's definitely the rule you want to know. Julia, that's an awesome question. Whoa! Okay, I just answered that question, so hopefully it's good to go. Okay, good. I'm glad that helped, Julia. And then Catherine, to answer your question, it's not only that there's more collisions, it's that when you have that increased energy, speed collisions. So at the higher energy, it's like you've got cars moving at 100 miles an hour at each other. That collision is going to do a ton of damage. So you're more activation energy barrier because you've increased the speed and energy at which that collision is happening. Or temperatures, what's doing is it's like taking cars that are moving at like 5 miles an hour. That collision is not going to be very energy. If you have a really high activation energy barrier with molecules moving really, really slow, you're not going to have enough of them hitting with the right energy to make products, which is why those of you that did temperature reactions in your rate lab, you saw that when you put them in those ice buckets, the reaction really, really, really slowed down because those molecules are moving so slowly. Also, thank you all for the well wishes for my husband. We were really happy that he's doing pretty well. He's doing a lot better than we thought he was going to be doing at this point, so that's awesome. All over the map, I apologize. Okay, so I answered your question, Catherine. Julia's good to go. All right, let's move on to question number 3. KEQ for a chemical reaction. So that would be like, let's go ahead and clear this out here. I'm going to pull in, what would that be in? I think you guys have practice problems with that. Let's go to my drive. KEQ this week with Mr. Summers. I hope that he's doing a good job at this place. He's a super nice. Gotta love it when the Wi-Fi works well, right? Action. And my computer's freezing. Okay, I'm just going to pull it up. We're just going to make it. O2. I'm going to write the KEQ. That remember, when you're writing KEQ, you cannot include solids and liquids. We only include aqueous and gases. And when we write KEQ, you put the products over the reactants. And so we have to make sure that this is balanced. Okay, so in my KEQ, what I would do to just write the general expression is you put your reactants. This is like a terrible number 2. I'm going to fix this. Looks like oh, that's not the eraser. All right. You put the products over the reactants, and then the coefficients become the power. Pen, come back. All right, that's 2H2. So how I'd write my KEQ expression is I would have the concentration of O2 over the concentration of H2 squared over the concentration of H2O2 squared. So that's how you'd write your KEQ. So essentially what this tells me, it's whatever my concentration of O2 is at equilibrium times the concentration, whatever my concentration of H2 is at equilibrium squared over the concentration of H2O2 squared at equilibrium. Could determine kind of what side is favored at equilibrium, because if you remember back to the video you guys watched, we talked about the collisions between the people, where if they hit hard enough, the arm will get transferred to the nose and vice versa. So at some point, you're going to have the rate of the forward reaction equal the rate of the reverse reaction, and that's going to be when equilibrium is established, when those two reactions are happening at the exact same rate. And at that point, the concentration that you have of the substances is going to remain unchanged. It's not going to, we're going to see that reaction in terms of what we visually see stop, because the total number of reactants and products is not changing, even though we are still having collisions at the microscopic level. So if we were to collect data, our number would remain constant at the point that equilibrium is established. So let's just pretend, I'm just going to make up numbers. It's definitely going to be a random problem. So let's just pretend at equilibrium, I've got 3 of these, I've got 1 of these, and I've got 2 of these. Let's just pretend that's what I have. So how I would calculate KEQ is I would sub these numbers into my brackets. So I'd have a 1 for oxygen, and then these are multiplied by each other. So I'd have times 2 squared, 3 squared. And you would just simply do that in your calculator. So you would just do, because I can't do math this late at night, nor can I do math half of my life, I would just do 4 divided by 9, which in this case would be 0.44. And so that would be my equilibrium constant. That would be my KEQ, 0.44. And what that would tell me is, because this is a decimal, that my bottom number is bigger than my top number, because it's a decimal place. So I've got a small number on top and a big number on the bottom. So what that would mean is that when my equilibrium is established, I have more of these pieces present in the reaction mixture. So I would have what's called a reactant-favored equilibrium, where I have more reactants left at equilibrium than I have products. So the general rule of thumb when you're looking at KEQ is that if your KEQ is greater than 1, it means you have more products. If your KEQ is less than 1, it means you have more reactants. And if your KEQ is exactly 1, not some decimal, exactly 1, it means that you have equal numbers of products and reactants. So if you kind of think of it kind of like visual in terms of like number of pieces, if you had, let's say, something that had a full circle for the reactant, so that was an empty circle for the products, a KEQ that was bigger than 1, which has lots of products, would have lots and lots and lots of empty circles and maybe only 1 full circle. A KEQ that was reactant favored would have lots and lots of full circles and maybe only 1 empty circle. And then a KEQ that was exactly 1 would have the exact same number of products and reactants. So calculating, you just write out your KEQ expression using your coefficients as powers, and then you would go ahead and plug in whatever numbers the problem gives you. So I hope that helps a little bit. Let's go back to the doc. I hear some questions coming in. Okay. Okay, so Julia, yes, if it has solids or liquids, you don't put that in the KEQ expression. The KEQ expression only has solids and liquids. To Jenna, I knew what to square because of the coefficient. So whatever the coefficient is in your problem, so there's any questions on here, whatever the coefficient is in your balanced reaction, that would become the power. So if we had something, if we go back to the example like, let's go back to that whiteboard. Let's just do one that has solids and liquids in there. What would be something that would be, let's do this. Okay, so let's do Na, let's go Na2CO3 plus, no, that's a bad one. Let's do, oh yeah, let's do this. Let's do AlCl3 plus AgNO3 goes to AgCl plus AlNO3. And then this would be a 3 here, and this would be a 3 here. So this would be aqueous based on solubility rules. This would be my solid, and this would be aqueous. So if I'm writing the equilibrium expression for this guy here, aqueous stays, solid does not go in my KEQ, and aqueous stays. So for this one, my KEQ would just be the concentration of my AlNO3 over the concentration of my AlCl3. Oh, that should be a bracket. Times the concentration of my AgNO3. And then that would be cubed. So whatever your coefficients are, that's what becomes your power. Because this is a solid, solids don't get included. So anytime you see a solid, just cross it out. Anytime you see a liquid, cross it out. Your KEQ only includes things that are aqueous or things that are gases. And then coefficients become powers. So I hope that that answered Julia's question. And I believe it was Jenna's question. So Eliana, it only works with aqueous and gases, not solids and liquids. So I hope that helped you guys there. All right. So KEQ states of matter included are aqueous and gas. Not included are solids and liquids. And then KEQ, remember KEQ greater than 1. Ooh, that's not E. Then 1 equals more products. KEQ less than 1 equals more reactant. KEQ equals 1 means equal, oh my gosh, reactant and product. Okay, so I hope that helps the KEQ type stuff. Liz, to go back to how you find your thing, if it's aqueous or not again, you have to use the solubility rules, just like Nathan J said. You have to use the solubility rules in the back of your periodic table. So you start with the negative ion, follow over to see what it's hooked up with, and that will tell you whether it's soluble or not soluble. And the idea that this comes down to, guys, where it's KEQ greater than 1 more product, KEQ less than 1 more reactant, comes down to the idea that it's a fraction. So if we think about the number, if the number is greater than 1 over here, that means this top number needs to be bigger, which means there needs to be more products. For this number to be less than 1, it means your bottom numbers need to be bigger, which means there needs to be more reactant. So that's how we get that kind of idea. So if you've got a number bigger than 1, it's because the top of your fraction is bigger, so more product. If you've got a number less than 1, it's because the bottom number on your fraction is bigger, which means you've got more reactant. That's how we get that idea. All righty. So I just did that guy up here. So I'm going to go ahead and move him up here. Because I did that guy already. Boom, boom. Okay. Okay, for this one, 6, I kind of already hit this guy here, the idea of chemical equilibrium. If you're struggling with that idea, I would watch that TED Ed again. This TED Ed does an awesome job of kind of visually showing what equilibrium means. There's also a ton of great YouTube videos out there, or animations that do a good job of showing you what chemical equilibrium really means at the molecular level. It's really, really hard to describe with words. It should be the first link in that review activity that that you did, Julia, where the TED Ed video is. It should have been that very first link that you watched in the equilibrium video that was posted in Google Classroom. So it should be, let me go here. Julia, I was just in your end of unit notes. It should be in, if we look at this guy here. Steven, I'm opening up your guy. Sorry if you're on. I'm going to judge your answers. Yeah. So I'm not going to play this now, but I'm just going to link it. It's the that I am talking about. It's linked right here, guys. So this is the video that I would watch. Look harder. You guys, Ryan, you're so mean to Julia. Be nice to Julia. Okay. I'm going to move this guy up here. That was really random. Okay. All right. Why does diluting increase solution speed on chemical? All right, I'm going to pull in a picture of diluting a chemical reaction right now. Okay. What does this picture look like? Oh, I'm ready. That's a terrible. Okay. So we think about diluting. Diluting means to water down. So if we had a substance that we had not diluted, so this was our stock solution, let's say. So many pieces. Okay, so that'd be the number of pieces in our picture, right? But if I dilute it and I add more water, what happens is you have the same number of pieces, but then they're now just a lot more spread out. So what diluting something does is it takes something that was super, super compact and concentrated in a smaller volume and spread out in that larger volume. So if we think about the idea of collision theory, what diluting something does in a chemical reaction is it gives more space for the reaction to take place, which is not a good thing. When we want chemical reactions to occur quickly, we want there to be a lot of collision. So the easiest way to do that is to take something and keep it super, super concentrated. Keep that amount of substance really, really high in a small space. When we start to add water to that, it spreads out the space that the stuff can live in. So it's going to decrease the number of collisions occurring, which is going to then decrease your rate because you've got less collisions, which means you've got the right activation energy and orientation, which means less product are being formed. So diluting something just spaces out all the pieces that you need to be colliding, which does not help us react faster. That's a really terrible picture, but I hope that helped. Oh, there's my Christmas labels. Okay. So I hope that helped. RST, you're correct, for sure. You have to have a collision with the right orientation and energy. Okay. And then for this last one here, where the 3 requirements that must be met in order for a chemical reaction to occur, you have to have a collision at the right orientation and right energy. Cool. And just when we think about ways to impact rate, pretty much what we're doing is you're trying to make these things happen better to make the reaction go faster, or make these things happen worse, which would make the reaction go slower. That's kind of what you guys investigated in your labs. Like we talked about diluting again, diluting is going to space everything out. So you've got less collisions, meaning less are happening at the right orientation, less are happening at the right energy, all that kind of stuff. And that's where we're at. It's of chaos and talking. I am to, oh, I see someone who's typing in a question now. We'll go ahead and answer this here in a second. Julia, no problem. I'm happy that I'm able to help you guys. Thanks, Liz. I miss you guys, honestly. I honestly do miss you guys. My husband says, hey, he hopes you guys do really well in the final. I am going to try and be at the library for the first hour tomorrow night between 4 and 5 to help you guys out if you've got a few more questions. if anything comes up tomorrow while you're reviewing with Mr. Summers, please write that down. And if you can get to the library, I'll be there. If you can't get to the library, please feel free to email me your questions. I can't promise I'll get back to you right away tomorrow evening, but I probably will get back to you once my daughter goes to bed, which is between 8 and 8:30. So that's kind of where we're at. You guys are hilarious. No, Liz, it's not the school library. It's at Aspen. Of course, guys. Seriously, no problem. Do not give my stream a like. This was maybe the worst video I've ever made. Okay, I'm going to answer this one, and then if you guys have no other questions, let me know. The graph to the right shows the formation of product or the conception of reactions. Explain your answer. Okay, so this guy here, if we think about this, it's all about slope. All right. So if we are trying to figure out if a graph is showing reactants versus products, you want to look at the slope. Because this slope is negative, that means you're starting with a lot of stuff and it's going to decrease over time, which means this is looking at your reactants being used up. So negative slope means reactants used up, which positive slope means that it would be products made, just like those of you who actually graphed bubbles in your rate lab like you were supposed to, or from the hydrogen peroxide graph, we were counting bubbles of gas that had a positive slope because we were looking at products made. So negative slope means reactants used. Positive slope means products made. And that's where we're at. So if you guys have any questions left, go ahead and pop them in the chat. Guys, I'm going to sign off here probably in a couple of minutes, and I'll see some of you guys tomorrow at the library. So yeah. Thanks for watching. You guys are going to do awesome. I know it. You guys are going to kill the final. So close this out. Clear this out. All right, I'm going to go ahead. I'm going to stop the broadcast. So I hope you guys do an awesome job. Good luck on the final. You guys are going to kill it. I will talk to you later, guys. Oh, and that's my box of Christmas. I'll show you guys this at the end. Those of you who are still streaming. This is my super cute Christmas card. You can all be jealous. That's right. I'm going to leave you with this. Happy holidays from Mrs. Etnine and her super cute family. That's my daughter. She's so cute. All right, guys. Have a good night. Good luck on your final.